In this demo video, let us investigate how to use the periodicity condition for AC magnetic simulations. Let's create a simulation project. And then I don't have a step file here, but I can easily draw the test geometry. So let me start drawing a box right away in the browser of given dimensions. This will be followed by a cylinder with default properties and then another cylinder of smaller dimensions. There we go. Now, I want to delete the parts that I'm not interested in, so I could first break the geometry into pieces, fragment it, and then I will be able to remove these two parts that I'm not interested in, just construction parts. And I'm left with a 90-degree sector of, you have to imagine, 4 macroscopic conducting cables. Very macroscopic. This is just an illustration. Let's define materials. Let's choose air here, and then we will also say that we have an aluminum cable, thick cable here inside. And we can move on to the physics. We could use only the H formulation, but this has the disadvantage that it requires to make the air slightly conductive, although it's an insulator. So we have something much better than that. We have the H-phi formulation. So in the phi, it's a magnetic scalar potential. This is where we put all the non-conducting region, perfect insulator. And in H, this is where we will put the conducting region. Then let's set up phi. So we have to have a unique solution. So we have to do the very common thing of gauging phi, setting the reference to 0 somewhere. Somewhere it's better not to put it on the periodicity condition, but here's going to work just fine. And then we need to drive a current through this aluminum cable. So we can select a closed loop around the cable and use the right hand to know in which direction the current will flow. So here in the plus Z direction. And we want to drive here with currents with sinus 2 pi ft, which for the harmonic analysis we do here, this will be the real part of at the fundamental frequency with a 1 amp drive. Next thing is set up the periodicity condition. So here it's a rotation condition, and the rotation center will be 0, 0, 0. Z-axis doesn't matter here. And the rotation angle will be 90 degrees in the Z direction positively as we go from the first phase here to the second phase here. Next, we set up the H physics. For that, we simply have to say that we have a H-phi coupling. This will add the right equations to take the induced current in the conductor. We can now simulate this. We could explore different meshing options, but here we'll just pick, for simplicity, the fine mesh default. We want a harmonic analysis type, and I will just choose 50 Hertz fundamental frequency. Here it's just a demo. It doesn't make that much physical sense to have such big cable dimensions, but it illustrates very well how to use the periodicity conditions. We can inspect the mesh, which is refined a bit around the cable as you want to have it. And then we can also ask for what outputs we want to see. We could ask for lots of things. Here I will just illustrate by asking to see the real part of the magnetic field B. And we are ready to run the simulation. The simulation should be fairly quick to run. As soon as it starts, it will run quickly, then upload the results, and we will be able to visualize all this. So 5 seconds runtime here, no need to do any high performance acceleration. It's a small problem, and we can render immediately in the browser. So for example, we might be interested to see the glyphs with some size that fits what we want to see. So some bigger glyphs than the default. And what do we see? Well, we have magnetic field flowing around the conductor, and the periodicity condition is nicely enforced, so you can see that the magnetic field flows from here and exits here in a periodic way. That's it for this demo. See you in another demo. Thanks you for watching.